So, back again with another video. Hope you had a good Thanksgiving break. We are going to start now with chemical reactions, which is going to feed directly from what we did about coming up with these symbols, because as you'll see, chemical reactions are going to be expressed in terms of. So first of all, a little refresher, what is a chemical reaction? Well, you'll recall that a chemical reaction is when one substance changes into another substance. This is what we call a chemical reaction. Now again, let's be very clear here. We're not changing an element into another element. You can't do that in chemistry. You can in physics, but you cannot do that in chemistry. We'll be moving elements from one compound to another typically. If there's going to be a chemical reaction happening, look for the following things: light, heat, production of a gas, a color change, or the formation of a precipitate. And a precipitate is a solid forming from a reaction between two liquids. And a reaction may be written in the form of an equation, and that's what we're going to work on mostly today. So, what does an equation look like? Well, something like this. You'll notice it does bear some similarity to a math equation. There's an arrow sign that's going to be your equal sign. There's pluses here, so that's similar to math, but there the similarity really ends. So let's look through this real quick. Think back to before Thanksgiving and see if you can name all of these things. This one will be a little bit tricky here because here's a polyatomic ion, and those did not go so well. So in other words, what we have is solid sodium is going to react with liquid water to form sodium hydroxide and hydrogen gas. Okay, a few notes here. Reactants are on the left side. This is what we start with. The arrow is an equal sign. That's where this word form comes in. You could also say yields. You could also say produces, something like that. And the products, what we end up with, are going to be on the right-hand side. Also, in this equation up here, we have the states of matter listed. Subscript, in parentheses, down here near the bottom right-hand side. If it's an S, it's a solid. L is going to be a liquid, specifically a pure liquid, not with something else mixed in here, so this is pure water. G is gas, and then this AQ here, let's see, what could AQ be? AQ, similar to the Latin word for water, from which it comes from, is going to be aqueous, like agua, water. Specifically something that's dissolved in water. Specifically, this is going to refer to ionic compounds that dissolve in water. These are going to be things that are going to be aqueous. Because sodium hydroxide, if you throw it in water, it's not going to stay a solid. It may be a solid crystal outside of water, but you throw it in, it will dissolve, just like salt. Salt water is an aqueous solution. A few clarifications regarding balancing equations. First of all, if we go back real quick, you will see that I called this hydrogen, not dihydrogen. We already had enough stuff last chapter that I didn't want to throw this in and confuse you, but there are some molecules that are called diatomic molecules. By diatomic, it means two atoms. So a lot of these, if we say oxygen gas, that's always going to be O2. If we say fluorine, that's always going to be F2. There are certain things that always, if it's a pure amount of it, it's going to be a covalent compound with one other of the same type. How do we know what they are? Well, there's 7 of them, and there is a little mnemonic to help remember this. Dr. Hinkelbroff. Dr. Hinkelbroff. In other words, hydrogen, iodine, nitrogen, chlorine, bromine, oxygen, and fluorine. Anytime you hear one of those, it's always going to be with another one in a covalent bond. We'll practice that over the course of this unit. Few other notes. The states of matter can be hard to predict. Again, going back to the last slide, how, for example, would you know that the hydrogen here would be a gas and not a liquid or a solid? Well, we can oftentimes predict that because you know that hydrogen is a gas at room temperature. Most reactions are going to be taking place at room temperature. But sometimes you'll get gaseous water as a product. How would you know that it's gaseous? Just look for how much heat is produced. Oftentimes these reactions will produce a lot of heat, and that's going to boil water or some of these other things. But again, we will practice with this too. Another thing that we didn't touch on this last slide, the number of atoms on the left side in the reactants have to always equal the number on the right side in the products. This is very important because this is going to be involved in balancing reactions, which is what we're going to move to next. Let's go back again and take another look at this one. So there's one sodium over here, and there's one sodium over here. There's one oxygen over here, and there's one oxygen over here. But there's two hydrogens here, and on this side we have two hydrogens, and then another one hydrogen, three hydrogens. This violates what we know of chemistry. Because the reactants must equal products, you'll remember that this is due to the law of conservation of matter, one of these things that Antoine Lavoisier in the late 1700s worked out. We cannot make matter, we cannot destroy matter, so if there was a change, it has to be balanced. It has to be balanced. This is going to be important later for determining mole ratios, which will allow us to make predictions starting in January. We're not going to have to worry about that now, but predictions, for example, such as if you start off with 20 grams of sodium in that previous reaction, how much sodium hydroxide will you make? So we're going to balance by using coefficients, and coefficients is used just the same here as it is in math. It's going to be a big number in front of the compound, in front of the compound. A few tips about balancing. Balance only one type of atom at a time. Don't try to balance the whole thing. Just pick one atom, make sure it's balanced, and move on. 2. Start with atoms that only appear once on each side. Save oxygen and hydrogen for last. And double check that everything is balanced correctly when you finish, because sometimes something will have been balanced before, but if you go back and balance the oxygens, now it's not balanced. If you haven't done this before, I know some of you have done this in middle school, but it may sound sort of confusing. So let's try one. Let's try the electrolysis of water. What is meant here is that you take water, pure liquid water, we'll see here, you run electricity through it, and it's going to break up into hydrogen gas and oxygen gas. You can do this by as simple as dropping a battery in water, for example. Well, let's go ahead and try to balance this thing. Count up the hydrogens on the left and count up the hydrogens on the right. On the left, we have 2 hydrogens. On the right, we also have 2 hydrogens. Okay, so are those balanced? Yes, hydrogens are good. Let's take a look at oxygens. How many on the left? 1. How many on the right? 2. So that's not balanced. How are we going to have to fix this? Well, we're going to have to put a 2 in front of here, because if we put a 2 in front of here, and I know this isn't drawing on the screen, but just pretend that it is, then we can multiply that through, and we'll have 2 oxygens here and 2 oxygens here. The oxygens are great now. Is everything balanced now? Well, not exactly, because now there are too many hydrogens. If we put a 2 in front of here, now we had 2 hydrogens before, but now we're saying we have 2 water molecules, so that's 2 times 2, that's going to be 4 hydrogens, while we only have 2 over here. So now we're going to have to balance the hydrogens. In order to balance that, we can very simply put a 2 right here, giving us 4 on that side. So our final balanced equation will look like this. 2 water molecules will break up to form 2 hydrogens and 1 oxygen. We don't have to put the 1 in front of here, just like in math, you don't have to put a 1 in front of x if you've just got 1x. I guess you can if you want to. It's sort of a waste of time. So we can double check that here. We've got 4 hydrogens here because we had H2 times 2, so 4 hydrogens, 4 here, and then 2 times 1, 2 oxygens, and another 2 oxygens. And you're done. We will practice this in class. You also need to practice it for homework. You also need to read chapter 8 of the book. These are very important things to do. What we're doing in class, while it's useful, it's not enough. You are going to have to practice on your own as well. I would suggest going back to the sodium and water reaction that we did earlier in the slide. See if you can balance that. We'll go over that next time in class, but I think if you balance it by yourself, that will also help you to gain a little bit of insight onto how this is done. See you next time.